Hello students, welcome to the lecture on number system. And after the lecture we will be able to learn the following objectives. Explain the digital and analog operations, understand the binary data, define the binary number system, describe the decimal number system, describe the octal number system, define hexadecimal number system, discuss the coding system, describe the error detecting codes. Let's start with a brief introduction to number system. 1, 2, 3, 4, 5, 6, 7, 8 and 9. The computer uses binary digits for its operation. In the binary system there are only two digits, 0 and 1. The programmer feeds instruction and data in alphabets and decimal digits, but for the operation of the computer these are converted to binary bits. Computer circuitry is usually designed to process hexadecimal or octal number. Number systems are two types, non-positional number system and positional number system. Non-positional number systems, this method of counting uses an additive approach or the non-positional number system. In this system, we have symbols such as 1 for 1, 2 for 2, 3 for 3, 4 for 4 and 5 for 5, etc. Each symbol represents the same value regardless of its position in the number, and the symbols are simply added to find out the value of a particular number. Positional number systems. In a positional number system, there are only a few symbols called digits, and these symbols represent different values depending on the position they occupy in the number. The value of each digit in such a number is determined by three considerations: the digit itself, the position of the digit in the number, and the base of the number system. Example: decimal, binary, octal, hexadecimal number system. Let's now discuss the meaning of digital and analog operation. There are a variety of other methods for digitalizing analog signals. The most important single reason for investigating other methods of conversion is to determine ways to reduce the conversion time. Recall that the simultaneous converter has a very fast conversion time. The counter converter is simply logical but has a relatively long conversion time. Successive approximation. The successive approximation method thus is the process of approximating the analog voltage by trying one bit at a time, beginning with the MSB. The ADC 0804. The ADC 0804 is an inexpensive and very popular AD converter which is available from a number of different manufacturers including National Semiconductor. It is capable of digitizing an analog input voltage within the range of 0 to plus 5 volt DC, and it only requires a single DC supply, voltage usually plus 5 volt DC. Section counters. Another method for reducing the total conversion time of a simple counter converter is to divide the counter into sections. Such a configuration is called a section counter. To determine how the total conversion time might be reduced by this method, assume that we have a standard 8-bit counter. Binary data. With HTML5 comes many APIs that push the envelope on user experiences involving media and real-time communications. These features often rely on binary file formats like MP3, audio, PNG images, or MP4 video. The use of binary file formats is important to these features to reduce the bandwidth requirements, deliver expected performance, and interoperate with existing file formats. Typed arrays and array buffers. Typed arrays provide a means to look at raw binary contents of data through a particular typed view. Typed arrays for reading binary file formats. Typed arrays is to read and render the contents of custom binary file formats that are not natively supported by the browser. As well as the various array types introduced above, typed arrays also provide a data view object that can be used to read and write the contents of an array buffer in an unstructured way. This is well suited to reading new file formats, which are typically made up of heterogeneous mixes of data. Getting binary data with XHR and File API. Before we can use the typed arrays APIs to work with the contents of the files, we need to use browser APIs to get access to the raw data. For accessing files from the server, the XML HTTP request API has been extended with support for various response types. Binary number system. In the binary system, there are only two possible symbols or digit values, 0 and 1. Even so, this base 2 system can be used to represent any quantity that can be represented in decimal or other number systems. In general, though, it will take a greater number of binary digits to express a given quantity. All the statements made earlier concerning the decimal system are equally applicable to the binary system. The binary system is also a positional value system wherein each binary digit has its own value or weight expressed as a power of 2. Binary counting. Binary numbers restricted to a specific number of bits. This restriction is based on the circuitry that is used to represent these binary numbers. Decimal number system. The decimal system is composed of 10 numerals or symbols. These 10 symbols are 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9. Using these symbols as digitals of a number, we can express any quantity. The decimal system, also called the base 10 system because it has 10 digits, has evolved naturally as a result of the fact that man has 10 fingers. The decimal system is a positional value system in which the value of a digit depends on its position. The decimal counting. When we start the counting in the decimal system, we start with 0 in the unit's position and take each symbol or a digit in progression until we reach 9. Then we add a 1 to the next higher position and start over with 0 in the first position. This process continues until the count of 99 is reached. Then we add a first to the third position and start over with zeros in the first two positions. It is important to note that in decimal counting, the unit's position LSD changes upward with each step in the count. The tens position changes upwards every 10 steps in the count. The hundredths position changes upward every 100 steps in the count, and so on. Just as the decimal system with its 10 digits is a base 10 system, the octal number system with its 8 digits 0, 1, 2, 3, 4, 5, 6 and 7 is a base 8 system. The octal or the base 8 number system is a common system that is used with computers. Because of its relationship with the binary system, it is useful in programming some types of computers. Unit and number. The terms that you learned in the decimal and binary sections are also used with the octal system. The unit remains a single object and the number is still a symbol that is used to represent one or more units. Base, radix. As with the other systems, the radix or the base is the number of symbols that are used in the system. The octal system uses 8 symbols 0 through 7. The base or the radix is indicated by the subscript 8. Positional notation. The octal number system is a positional notation number system. Just as the decimal system uses powers of 10 and the binary system uses powers of 2, the octal system uses power of 8 to determine the value of a number's position. The following bar graph shows the positions and the power of the base. Let's now discuss the meaning of hexadecimal system. The hexadecimal number system is used as an intermediary system in computers, such as our presentation of memory addresses or a representation of colors. The hexadecimal number system is also known as the base 16 number system because each position in the number represents an incremental number with a base of 16. To determine what the actual number is in decimal representation, take the number that appears in the position and multiply it by 16x, where x is the power representation. For example, if a number appears in the furthest right position, take the number in the furthest right position and multiply it by 16. If there are multiple positions in the number, add all the results together. Fractional conversion. Numbers expressed in decimal number systems are much more meaningful to us than are numbers expressed in any other number system. Many methods can be used to convert numbers from one base to another. A method of converting from another base to a decimal and a method of converting from a decimal to another base are described here. Converting from another base to decimal. The following steps are used to convert a number in any other base to a base 10 decimal number. Step 1, you determine the column positional value of each digit. This depends on the position of the digit and the base of the number system. Step 2, you multiply the obtained column values in step 1 by the digits in the corresponding columns. Step 3, you sum up the products calculated in step 2. The total is the equivalent value in decimal. Converting from decimal to another base, division remained a technique. The following steps, they are used to convert a base 10 decimal number to a number in another base. Step 1, divide the decimal number by the value of the new base. Step 2, record the remainder from step 1 as the rightmost digit, least significant digit of the new base number. Step 3. Divide the quotient of the previous division by the new base. Step 4. Record the remainder from step 3 as the next digit to the left of the new base number. Repeat steps 3 and 4, recording remainders from right to left until the quotient becomes 0 in step 3. Note that the last remainder thus obtained will be the most significant digit of the new base number.
Now that we know the basics of how decimal numbers work, let's see how we can write some special fractions using decimal numbers. I'm going to call these fractions base 10 fractions because their bottom numbers are all powers of 10, like 10, 100, or 1,000. Let's start with this fraction, 1 over 10. Well, you should recognize that it's one of our building blocks, and this should be easy to write down as a decimal number because we have a number place just for counting tenths. So all we have to do is put a 1 in the tenths place, like this, 0.1. Now when you write decimal numbers, it's important that you always include the ones place. But since we don't have any ones, we just put a 0 in that spot. The 0 makes the decimal point easier to see. Alright, so that's 1/10. But what if we have 2 over 10 instead? Well, all we have to do is change the digit in the tenths place to a 2. So 2 over 10 equals 0.2. In fact, we can keep counting tenths like this. 3 tenths, 4, 5, 6, 7, 8, 9, and finally 10 tenths. But look what happened when we got to 10 tenths. Now we don't have a digit for 10, so we had to use the next number place over, the ones place. But that makes sense because if you have the fraction 10 over 10, that makes a whole and the value is just 1. Of course, we don't really need the 0 in the tenths place to write 1, but as long as the decimal point's there, at least we won't confuse it with 10. Alright, tenths are pretty easy, but what about hundredths? Let's start with the hundredths building block, 1 over 100. To write that as a decimal, we simply put a 1 in the hundredths place. We also need to put a 0 in the tenths place to act as a placeholder and show that we have no tenths. And we still need to put a 0 in the ones place as usual. Next, let's try 2 hundredths. For that, we simply put a 2 in the hundredths place. Let's keep on counting with hundredths just like we did for tenths. 3 hundredths, 4, 5, 6, 7, 8, 9, and 10 hundredths. But look what happened when we got to 10 hundredths. Just like before, we have to use the next number place to the left, the tenths place. This happens because any time you have 10 of a building block, they combine to form one of the next biggest building block. For example, 10 hundredths is a tenth, 10 tenths is a 1, 10 ones is a 10, and 10 tens is 100. Now the next fraction after 10 over 100 is 11 over 100. Now if you think about it, you'll see that 11 hundredths is really just a combination of 10 hundredths and 1 hundredth. Knowing that will help us write it as a decimal. Because a group of 10 hundredths is equal to 1/10, we put a 1 in the tenths place. And we still have that 1 hundredth left over, so we put a 1 in the hundredths place. There, 11 over 100 is just 0.11 as a decimal. Fortunately, you don't have to break up the fraction into tenths and hundredths each time. Anytime you have a 2-digit number over 100, all you have to do is put those digits into the tenths and hundredths place of your decimal number. Let's look at a few more examples to help you see the pattern. 24 over 100 would be 0.24. 32 over 100 would be 0.32. 78 over 100 would be 0.78. And 99 over 100 would be 0.99. Now what do you think will happen if we convert the fraction 100 over 100 into a decimal? Right, 100 has 3 digits, so we need to use another number place. Now the next one over is the ones place. And that makes sense because 100 over 100 is a whole, and its value is just 1. Now that we know how to convert hundredths into decimals, let's try converting thousandths. That's fractions that have 1,000 as the bottom number. Let's start with 1 over 1,000. Now this should be easy. All we have to do is put a 1 in the thousandths place. Notice that this time we need zeros in both the tenths and the hundredths place to act as placeholders. Next, let's try converting 10 over 1,000. Remember that 10 thousandths is the same as 1 hundredth, so we'll put a 1 in the hundredths place, and we'll put a 0 in the thousandths place. We don't really need the 0 at the end, but it helps us see that this was 10 thousandths. Alright, what if we have 100 over 1,000? Now that's a 3-digit number on top, so we're going to need to use 3 number places. The thousandths place, the hundredths place, and the tenths place. So as you can see, 100 over 1,000 is just the same as 1/10. Let's see a few more examples. 58 over 1,000 is 0.058. 73 over 1,000 is 0.073. 365 over 1,000 is 0.365. And 999 over 1,000 is 0.999. And finally, What do you think we would get if we converted 1,000 over 1,000? Right again, 1,000 over 1,000 is just a whole, so its value would be 1. Okay, so we've learned how to convert base 10 fractions into decimals, but we can go the other way too. We can start with a decimal and convert it into a fraction. Let's say we want to convert a decimal number into a fraction. All we have to do is take the decimal digits and make them the top number of a base 10 fraction. The bottom number will be determined by the smallest number place used in our decimal. For example, to convert 0.8 into a fraction, we put an 8 on the top and a 10 on the bottom because the smallest number place in our decimal was the tenths place. And to convert 0.29 into a fraction, we put a 29 on top and we put a 100 on the bottom because the smallest number place in our decimal was the hundredths place. And finally, to convert 0.568 into a fraction, we put 568 on top and 1,000 on the bottom because the smallest number place in our decimal was the thousandths place. Okay, so far all of the fractions that we've converted to decimal numbers and vice versa have bottom numbers like 10, 100, or 1,000. Those fractions are easy to convert because our number system is based on powers of 10.
Now converting from a base other than 10 to another base other than 10. The following steps they are used to convert a number in a base other than 10 to number base other than 10. Step 1, you convert the original number to a base or a decimal number. Step 2, convert the decimal number obtained in step 1 to the new base number. Shortcut method for binary to octal conversion. The following steps are used in this method. Step 1, you divide the binary digits into groups of 3 starting from the right. Step 2, convert each groups of 3 binary digits to one octal digit. Since there are only 8 digits 0 to 7 in octal numbers, number system 3 bits 23 equals to 8 are sufficient to represent any octal number in binary to decimal conversion method in this step. The shortcut method for octal to binary conversion. The following steps are used in this method. Step 1, convert each octal digit to a 3-digit binary number. The octal digits may be treated as decimal numbers for this conversion. Step 2, you combine all the resulting binary groups of 3 digits each into a single binary number. Shortcut method for binary to hexadecimal conversion. The following steps are used in this method. Step 1, you divide the binary digits into groups of 4 starting from the right. Step 2, you convert each group of 4 binary digits to one hexadecimal digit. Remember that hexadecimal digits 0 to 9 are equal to decimal digits 0 to 9 and hexadecimal digits A to F are equal to decimal values 10 to 15. Hence, for this step, you use binary to decimal conversion procedure and represent decimal values 10 to 15 as hexadecimal A to F. Shortcut method for hexadecimal to binary conversion. The following steps are used in this method. Step 1, you convert the decimal equivalent of each hexadecimal digit to a 4 binary digit. Step 2, you combine all resulting binary groups, 4 digits each, into a single binary number.
We'll be going over dividing decimals. Here we have 31.773 being divided by 5.1. So let's set this up using long division. We have 31.773 on the inside being divided by 5.1. And the one thing that you have to remember, and I wrote this for you in green, you have to get rid of the decimal in the outside number. So we have an outside number of 5.1. We need to get rid of this decimal in the outside number. So basically we have to push this decimal point as far right as possible. In this particular example, we only can push it over one space. And whatever you do to the outside number, you have to do to the inside number. So since we moved our outside decimal one space to the right, we have to do the same thing to the inside decimal. So now, since we moved both decimal points one space to the right, our 5.1 becomes a 51, and our 31.773 becomes 317.73. So 31.773 divided by 5.1 is exactly the same as 317.73 divided by 51. So now I'm just going to give myself a little bit more space and erase this on the top. And I'll move this a little farther up. So now that we got rid of the decimal in the outside number, we can just divide this using normal long division. So let's just get started right away. 51 goes into 3 0 times, since 51 is bigger than 3, so we'll move to the next digit. 51 goes into 31 0 times, since 51 is bigger than 31, so we'll move on to the next digit. 51 goes into 317 how many times? Well, we know that 50 goes into 300 6 times, so I'm going to guess that 51 goes into 317 about 6 times. So now if we multiply the 6 times 1, we get 6, and 6 times 5 is 30. And if we subtract the two numbers, we get 7 minus 6, which is 1, and 1 minus 0, which is just 1. And I'll bring down my 7. So 51 goes into 117 how many times? Well, we know that 50 goes into 100 2 times, so I'll guess that 51 goes into 117 about 2 times. And 2 times 1 is 2, and 2 times 5 is 10. So 7 minus 2 is 5, and 1 minus 0 is just 1, and bring down my 3. And before I go any further with this example, I want to place our decimal point. Our decimal point just needs to move straight up, so it goes directly in between the 6 and the 2. So now how many times does 51 go into 153? Well, we know 50 goes into 150 3 times, so I'll guess that 51 goes into 153 3 times as well. 3 times 1 is 3, and 3 times 5 is 15. So 153 minus 153 is 0. So we have a remainder of 0, which means that we can stop. So now we divided 31.773 by 5.1, and we have a final answer of 6.23.
Coding system. To represent numeric, alphabetic, and special characters in a computer's internal storage and on magnetic media, we must use some sort of coding system. In computers, the code is made up of fixed-size groups of binary positions. Each binary position in a group is assigned a specific value, for examples 8, 4, 2, or 1. Extended binary coded decimal interchange, code EBCDIC. Using an 8-bit code, it is possible to represent 256 different characters or bit combinations. This provides a unique code for each decimal value 0 through 9 for a total of 10. Each uppercase and lowercase letters for a total of 52, and for a variety of special characters. Each group of the 8 bits makes up one alphabetic, numeric, or special character and is called a byte. American Standard Code for Information Interchange, ASCII. Another 8-bit code known as the American Standard Code for Information Interchange, ASCII, pronounced ASCII, was originally designed as a 7-bit code. Several computer manufacturers cooperated to develop this code for transmitting and processing data. The purpose was to standardize a binary code to give the computer user the capability of using several machines to process data regardless of the manufacturer. Parity bit. The parity bit, also called a check bit, the C position in a code, provides an internal means for checking the validity, the correctness of code construction. That is, the total number of bits in a character, including the parity bit, must always be odd or always be even, depending upon whether the particular computer system or the device that you are using is odd or even parity. Therefore, the coding is said to be in either odd or even parity code, and the test for bit count is called a parity check. Now let us talk about error detecting codes. Error detection and correction, EDAC, or error checking and correction, ECC, a collection of methods to detect errors in transmitted or stored data and to correct them. This is done in many ways, all of them involving some form of coding. The simplest form of error detection is a single added parity bit or a cyclic redundancy check. Multiple parity bits can only detect that an error has occurred, but also which bits have been inverted and should therefore be re-inverted to restore the original data. The more extra bits are added, the greater the chance that multiple errors will be detectable and correctable. Parity check. One error detection bit whose value depends on the count of ones in the input. Even parity, bits selected to provide for even number of ones in the transmission, or parity, for an example, add a parity bit to each character. Cyclic redundancy check, or CRC. Add n bits to each block of k bits so that the n plus k bits will be divisible by a predetermined number. Module 10 arithmetic check digit method. Make number divisible by 9. Hamming code. When data is transmitted from one location to another, there is always the possibility that an error may occur. There are a number of reliable codes that can be used to encode data so that the error can be detected and corrected. With this project, you will explore a simple error detection correction technique called a Hamming code. A Hamming code can be used to detect and correct one bit change in an encoded code word. This approach can be useful as a change in a single bit is more probable than a change in 2 bits or more bits. Now in the end, let us summarize what we have learned in this lecture. The ADC0804 is an inexpensive and very popular AD converter which is available from a number of different manufacturers, including the National Semiconductor. Typed arrays provide a means to look at raw binary contents of data through a particular typed view. Each array type is a view over an array buffer. The array buffer is a reference to the raw binary data, but it does not provide any direct way to interact with the data. The binary file inspector demo uses data view to read the PCX file format and render it using a canvas element. The decimal system is composed of 10 numericals or symbols. These 10 symbols are 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9, using these symbols as digitals of a number. The hexadecimal number system is used as an intermediary system in computers, such as a representation of memory addresses or a representation of colors. Numbers expressed in decimal number system are much more meaningful to us than are numbers expressed in any other number system.